In this chapter, we will talk about physical quantities and their measurements. First, let's talk about the physical quantities. Science is a systematic enterprise to study the properties of matters. If a property describes a state of physical system, it's a physical property. Typical physical properties are color, density, temperature, and so on. If a property determines the ways matters behave in chemical reactions, it is a chemical property. Typical chemical properties are heat of combustion, chemical stability, flammability, and so on. The properties which can be studied must be measurable. But we are more concerned of the properties which can be quantified. They are physical quantities. For example, we can use our finger to feel whether the water is hot or cool, but a thermometer can quantify the hotness of water, which is temperature. Color is another example. Red, green, and blue are qualitative descriptions, while wavelength is the physical quantity to describe colors. In contrast, beautiful, tasty, interesting, and happy usually do not have physical quantities, because they are hardly quantified. Time is a special physical quantity which has nothing to do with physical systems. The properties can be also categorized into intensive and extensive ones. Intensive properties are those independent of the amount or the size of the system. Examples of intensive properties are density and the temperature, while the extensive properties are those proportional to the size or the amount of the system. Examples of extensive properties are mass and heat capacity. There are also properties which are neither intensive nor extensive. For example, the surface area of a system doesn't necessarily double when doubling the size of it. It depends on how the shape changes. Another example is the resistor. The resistance doubles when the two identical resistors are in series. But if they are in parallel, the resistance halves. A physical quantity must have a magnitude and a unit. For simplicity, we only discuss scalars in this chapter. For the discussion of vectors, please refer to linear algebra and geometry. A unit is a definite quantity that is used as a standard. Any other quantity of the same kind can be expressed as a multiple of the unit. The magnitude is the ratio between the quantity and the standard. Pay attention that the magnitudes are pure numbers, but the quantities are usually not. For example, meter is a defined length. A length of 6 times of the meter is 6 meters. Here, 6 is the magnitude, while meter is the unit. For historical reasons, a physical quantity can have various units. For example, meter and inch are both units of length, while temperature can be measured in Celsius, Fahrenheit, and Kelvin. For easy calculation, we always use SI units in science. SI is the abbreviation of International System of Units in French. The SI system is a modern form of the metric system. It is coherent, so that you can convert between units easily. The SI unit is based on base units, derived units, and prefixes. The International System of Quantities defines 7 base quantities. Here, I list their names, symbols, SI units and unit symbols. The quantities shown in red are of high importance in physical chemistry. Please make sure you use the correct symbols for both quantities and units. To reduce ambiguity, the symbols of the quantities are written in italic font, while the units are non-italic. Pay attention to the unit of mass. Even though kilo looks like a prefix, kilogram is the base unit. Also pay attention to the unit of temperature, which is Kelvin. Other physical quantities can be defined from the calculation of base quantities, as well as their units. In this slide, I show some derived quantities and their units. The definitions show their relationship with other quantities. The units of the derived quantities can be also calculated from the definitions as well. For example, the area is the square of length. So, the unit of area is the square of the unit of the length. The unit of length is meter. The unit of area is square meter. By the way, it's better to use the negative power of the unit instead of the slash. Here, I show you some additional physical quantities, which are often used in physical chemistry as well. Something to pay attention here. Pressure and power share the symbol P, but they are different physical quantities. Similarly, energy and electric field strength share the symbol E. Such phenomenon is inevitable because there are much more physical quantities than the Latin and Greek letters. So, make sure you understand the meaning of the symbol every time you read and use a formula. Sometimes, the derived units are complicated. Thus, new units are introduced. They are also SI units. They are named after scientists who made a great contribution to those fields, such as Newton, Pascal, and Joule. Finally, the SI unit of concentration is mole per cubic meter, but the unit of molarity is mole per liter. It is called molar or m. Sometimes we need to deal with numbers whose absolute values are too big or too small. A better way to write them is to use a scientific notation. A scientific notation is the product of a number between -10 and 10, and the power of 10. For example, 0.35 is written as 3.5 times 10 to the -1. -796 is written as -7.96 times 10 to the second. However, how about 58,400? Is it 5.84 times 10 to the fourth? We will discuss it later. Another way to avoid very big or small numbers is to use prefixes in the units. Here, I show you some of them. The prefixes in red are very often used in physical chemistry. Please remember them. There are also some non-SI units, which are often used in physical chemistry due to historical reason. For example, 1 angstrom is 10 to -10 meter or 0.1 nanometer. It is the typical size of atoms. Liter and milliliter are usually used in chemistry to measure the volume of liquids. 1 liter is a cubic decameter. A milliliter is a cubic centimeter. Cubic centimeter is also written as cc, but it is abandoned in modern science, and is exclusively used in medicine today. Finally, degree Celsius is often used for its convenience. The change of 1 degree Celsius is identical to the change of 1 Kelvin. 0 degree Celsius is equal to 273.15 Kelvin. Here is an example of the relationship between cubic meter, cubic decameter, and cubic centimeter. Please pause here to check by yourself. Energy has several often used units. An electron volt, eV, is the work done to an electron when it is accelerated between 2 points with voltage of 1 volt between them. 1 eV is about 1.6 times 10 to the -19 joule. The energies in quantum mechanics are usually measured in electron volts. Hartree is the absolute value of the potential energy of the electron in a ground-state hydrogen atom. A Hartree is about 27.2 eV. Hartree is another often used unit in quantum mechanics. A calorie is the energy needed to raise the temperature of 1 gram water by 1 degree Celsius. The exact value of 1 calorie changes with definition because the heat capacity of water changes with temperature. So, calorie is not used in today's science. Come back to the numbers. There are some conventions in writing numbers. To write an exact number, a fraction representation must be used. For example, the potential energy of a harmonic oscillation is 1/2 k times square x. Here, the half is an exact number, so it must be written as 1/2. You cannot write it as 0.5. 0.5 and 1/2 have different meanings in scientific writing. Another example, the probability to have number 1 from a cubic dice is 1/6. To write an approximate number, a decimal representation must be used. For example, a length of 1.76 meter cannot be written as 44/25 meter. Again, 1.76 has different meaning form 44/25 in academic writing. Another thing to remember is to keep the first zero if the absolute value of the number is smaller than 1. For example, 0.123 cannot be written as 0.123. The last digit of a decimal number represents the precision of it. For example, my height is 1.76 meter. When writing this number, I'm sure that I'm shorter than 1.77 meter and taller than 1.75 meter. And I'm more likely a height between 1.755 meter and 1.765 meter. As a reader, when you read this number, you should also understand the same precision as I expressed. Another example, I wrote my weight to be 53.0 kilogram. By writing this number, I meant I'm lighter than 53.1 kilogram and heavier than 52.9 kilogram, and more likely between 52.95 kilogram and 53.05 kilogram. 53.0 kilogram has a totally different meaning from 53 kilogram. 53 kilogram means I'm sure I'm lighter than 54 kilogram and heavier than 52 kilogram, and I'm more likely between 52.5 and 53.5 kilogram. So, now you can understand the difference between 53 kilogram and 53.0 kilogram. The significant digits are the digits from the first non-zero digit to the last precise digit. For example, 4.803. The first and the last digits are 4 and 3, so it has 4 significant digits, 4, 8, 0 and 3. 0.00661 has 3 significant digits, 6, 6 and 1. 55.220 has 5 significant digits, 5, 5, 2, 2 and 0. The zeros at the end of the number but before the decimal point are confusing. For example, 58,400. The readers don't know which one is the last precise digit. Using scientific notation can avoid this ambiguity.